BC is parallel to AD, and BC is equal to AD. And we're supposed to prove, okay, let's mark that in red. BC is parallel to AD, that's already marked. And BC is congruent to AD. And we're supposed to prove BCD is congruent to DAB. Okay. Well, all we have is a couple of congruent sides, but then we start marking some stuff in orange. Remember, we have to prove it. We know BD is congruent to itself. Well, and parallel lines always give us some stuff with some transversals. So let's draw in the transversals and see what we got there. Okay, we'll do that in, let's do that in green, because green is different from everything else that we've got up here so far. We have some parallel lines here, and we have a transversal here, and so we can mark our alternate interior angles, because those are congruent and they're parts of the triangle. Now there are a lot of other things we can mark too, but they're not going to do us any good. So we only want the part that's going to help us with these triangles. And if we mark that, what are our choices of how to prove these are congruent? We have side, 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 angle, side, angle, side, angle, 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 side, and hypotenuse leg. We have side, angle, side. Okay, I got to get rid of that because I just wrote in red all over top of that stuff that I put there so I could find my way through this proof. Alright, so proof. Statements, reasons. Number 1, BC is parallel to AD, and that's given. Number 2, BC is congruent to AD, and that's given. Now earlier I put them all into the same given statement. That's okay too. It doesn't really matter. Alright, now we've already marked these two sides congruent. Now let's take care of these angles. Number 3, angle ADB is congruent to angle DBC, because if lines are parallel, then alternate interior angles are congruent. Number 4, BD is congruent to BD because it can see itself in the mirror. It's reflexive. And then 5, triangle. How do they do it? BCD is congruent to triangle DAB by side, angle, side. Wow, complete the proof. AC is the diameter of F. Okay, so the first one says AC is the diameter of circle F. Let's see what we're supposed to do. It's the diameter of F, and AC is perpendicular to BD. We've got that marked. And then we're supposed to prove AD is congruent to AB. Okay, so since we're just going to follow their proof, it says it's a diameter and all that stuff is put together in one statement. And that's fine. Given. Okay, now what's going to help us? What has to do with those arcs that has to do with all right angles are congruent? Well, I only see one right angle there, but if I look closely, I actually see there are 4. There are 4 right angles here, and it's telling me all right angles are congruent. I've got this right angle here, but that has nothing to do with one of those arcs. And I've got this right angle here, and that has nothing to do with either of those arcs. But this right angle, that has to do with this arc. So I'm thinking these 2 right angles must be what they're talking about. AEB is congruent to AED, because those are going to have to do with those arcs. Whoops. I erased given. Okay. I'm going to mark that stuff back. I didn't like the way that my arcs looked. Put that back in. Given. Okay, now we said the only right angles that had to do with these arcs were AEB and AED. So, angle AEB is congruent to angle AED because all right angles are congruent. And this symbol right here could mean that they're right angles, or it could mean they're perpendicular, because perpendicular lines make right angles. Whoops. Okay. Hope I don't make you sick doing that. DE is congruent to EB. Okay. This is a theorem that says that if the diameter of a circle intersects a chord at a perpendicular, then it bisects both the chord and the arcs. Ooh. Okay, so I want to kind of look up and see if that has a name. I know what it is, but the question is, what do we want to call that? And you've got, aha. It is on page 665. If the diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. I'm wondering if I can use that one because that's what we're trying to prove, sort of. So I'm not real sure if I can use that one or if there is another. What page did I tell you that was on? Oh, I can use it. Okay, that is the correct one. I just had to double check it. Okay, and this one, it does not have a name, but it's found on page 665, and it basically says if a diameter intersects, I'm going to use some abbreviation here, intersects a chord perpendicularly, it bisects it. And its arcs. Okay. So number 4 says AE is congruent to AE. Well, that one's pretty easy. Reflexive. A triangle AED is congruent to AEB. How do we do that? Let's see. We have, let me erase this stuff. Okay, what we just said was DE was congruent to EB. Did we say that? Right there. And we said AE was congruent to itself. And those are right angles. Is it hypotenuse leg? Well, here's the hypotenuse. And the hypotenuses are not congruent, so it's not hypotenuse leg. It's side, angle, side. So that's going to be by side, angle, side. Okay, then it says, what is going to be true because corresponding parts of congruent triangles are congruent? Well, what has to do with these arcs? That's what we need to find out. So look at this. What has any relationship to these arcs? The chords that correspond to them do. And those are each part of those congruent triangles. So AD is congruent to AB. That's what we're looking for. AD is congruent to AB. And that's because of Kapuktuk. Corresponding parts of congruent triangles are congruent. And then AD is congruent to AB because in circles with the same radius or in the same circle, if two chords are congruent, then their corresponding arcs are congruent. In a circle, if two chords are congruent, their T-H-E-I-R, I can spell even in math class, their arcs are congruent. Okay, and the whole point of me doing this with you is just to show you the process of reasoning that we're using here.